Good afternoon. It is my deep honor to speak to you today. And before I kick off, I just want to say, thank you for your time and attention. Quickly, look to your left, look to your right. These are the future leaders, right, in science and technology. And we are thrilled to share this time with you and look forward to how you innovate and bring a brighter future. Today, I am going to share with you a bit about my journey and focus on fusion as an incredible opportunity for alternative and clean energy. I'm a deputy director here in the high energy density division and senior scientist. I've been at SLAC for about a decade. And first and foremost, it is an incredibly exciting time in high energy density sciences and plasma sciences. And there's so many ways in which matter at extremes touches our life. My entry into all of this was actually in planetary sciences. So thinking about how planets actually form, that catastrophic impact event generates extraordinary pressures and temperatures, but sets up all the right ingredients for life. Do you know there's about 5,600 planets right now today that are these super Earths that have been discovered, of which small percent, 4%, are in the habitable zone, right? So it's about 200. Of those, 65 are in the super habitable zone. What does that mean? It means for over 4 billion years, there are planets just like Earth that are orbiting their sun, right? Which means all the right constituent materials for life and society as we know it could be taking place. It's just remarkable. But all of those components had to go through some extraordinary extreme event to get to where they are today. Thinking about novel materials, how we can construct, design materials to do or perform in certain ways for all sorts of technical applications, medicine, even the glass on the front of your phone, right? Aspects of that glass have been designed with purpose, and some of that comes through leveraging materials at extreme states to understand how to design at the atomic level these different materials. Planetary interiors, that's close to my heart. I have a different slide on that in a second. But thinking about over 6,000 kilometers below our feet, right? The Earth's mantle and core as the engine of our planet. And then where we'll go for the bulk of this talk, thinking about high energy density and in particular applications for energy, infusion energy as our frontier. So there are a lot of different ways to generate high pressure states. And so here's a fun graphic I like to share that sort of takes you through the mundane. How many of you had a soda or a canned beverage today? Raise a hand, right? So we know that you can keep the gas, the CO2 inside under a little bit of pressure, and then you release by opening the tab. So that's equivalent to about the amount of pressure exerted by a hammer when you hit it with a nail, or you hit the nail with the hammer, I should say. All the way up to other devices that are a little bit more, my graduate studies were leveraging something called the diamond anvil cell. So you take gem quality diamonds, you cut off the tip and oppose them, and these anvils can generate pressures up to the inner parts of our planet, the inner core, right? So just remarkable, like 3 million times our atmospheric pressure, and you can also apply heat and study the constituent materials of our planet, all the way up through what you can do with lasers and so-called Z-pinch machines, where you generate over a shorter period of time tremendous pressures that allow you to reach the conditions of our sun, the inner part of stars, and able to explore the fusion processes at play. Part of what I like to focus on, so many different tools. I'm an experimentalist, and so bringing to bear novel X-ray optical tools to probe, to interrogate these materials at extreme conditions. And you can set up these extreme conditions, a whole suite of different experimental apparatus. You can use shock waves. You can lower or increase the temperature, cryogenic to very high temperatures. Different radiation environments. And all of these have benefits in how we execute experiments, not just for discovery science, but also for applied science, and in particular, energy sciences. So what I'd like to do today briefly is share my journey through planetary sciences that led me to a place in fusion. And so the Earth is amazing. I've studied a lot of different aspects of the Earth, from the crust and how craters are formed and the minerals therein, to thinking about meteorites and actually how material was delivered to the planet. Do you know that all 5 of the nucleobases, right, that are in your DNA and RNA are actually found on meteorites, materials that have never been to the Earth, right? And it's been posited that one way in which life was actually kickstarted is through the delivery of material in a catastrophic, cataclysmic event in reaching the Earth's surface. And in those few moments of high pressure, high temperature, those prebiotic molecules build up complexity into something more complex, perhaps leading to life. So there's a whole discipline that is just waiting. These are questions, scientific questions that are just waiting to be answered. And so this is part of your exciting future. How many of you have felt an earthquake? Right here, yes, exactly. So understanding our the interior of our planet, just at that lower part of the crust, upper mantle, right, where rocks and materials engage with one another. Have you seen in the Hayward Fault? I've felt many quake along the Hayward Fault in the East Bay. And so understanding that profile of our planet, interpreting seismic tomographic images and the like. So all of this led to leveraging these unique tools, right? Generating extreme conditions and then probing with, today we'll talk about the LINAC coherent light source, leveraging these incredibly brilliant and coherent X-rays. So I started out simple beginnings, looking at the Earth, and now I say we're looking forward and trying to harness star power. And so the rest of this talk will be really focused on what we're doing today here at SLAC and our journey as a society into fusion energy. So if we look at the energy consumption recently, we understand that in 2050, with the onset of all the interest in different AI resources, data centers and the like, pushing toward other EV apparatus on the grid, we're going to need a way to support all of this energy consumption. And one way my colleagues and I think is a brilliant way to go is with fusion energy. But there's a lot of work we need to do. And so that's part of why I want to share this message with you today, and the advances that we're making. There was a watershed moment in December, just before Christmas in 2022, when a sister laboratory, the Lawrence Livermore National Lab. How many of you guys know about the Livermore Lab? Yep. Okay, so it's not too far away, bit of a drive in traffic. But over the many decades, they used the National Ignition Facility to perform physics tests on how to combine deuterium and tritium in a fuel capsule and compress them, fuse them together such that we get more energy out than we put in. And finally, after decades of effort, in December of 2022, they achieved this. This was truly remarkable. And it launched really a lot of exciting efforts in so-called inertial fusion energy programs. And since then, there's been an investment from private industry, upwards, I think it's around $8 or more billion to date, which is just remarkable. And that's probably an underestimate. So there's a lot of opportunity here. There's a lot of hype So we have to be thoughtful and critical and methodical in how we approach the science and engineering so that we can really deliver on this promise of a clean and reliable energy solution. Here at SLAC, we've undertaken a number of projects and programs to support inertial fusion energy, and the three main pillars of our effort, I'll just do it this way, focus first on advancing our understanding of laser matter interaction at extreme conditions. And some of this work allows us to move into the burning plasma regime, which I'll get to in just a bit. We need to understand what are the critical technologies that need to be de-risked for private industry to move from just a laboratory test, a one-off, example, into really performance driven routine orchestration for a future power plant, right? There are a lot of technologies that haven't been even established or considered. And so many of those we're working on here in-house. And furthermore, across the many different methods, concepts for fusion energy, materials really matter. And actually, I'll focus on that in a few slides. But the harsh environments, radiation environments from neutrons, from X-rays, building resilient materials, understanding how they will change in situ so we have predictive capability, right? We can be reliant on our codes, that's fine, as long as those codes are benchmarked, right? And part of that we lay at your footsteps moving forward. So, fusion. Fusion is, at its heart, what powers a star, right? We have two atomic nuclei that come together to form an entirely new nuclei. And in doing so, fusing these nuclei together, you release a tremendous amount of energy and a neutron. And there are different kinds of fusion we try to take from, have any of you seen there was a Spider-Man movie with Doc Ock, right? And he's got whatever in the garage or something, right? He's like, the power of the sun in your hands, right? Do you remember that? No kidding. That's what we're trying to do, okay? But we're doing it sort of step by step, and we have a lot of committees, and there's a lot of good discussion and papers, right? So we're trying to do it not like Doc Ock, but in a really methodical way, right? And so there are three flavors of fusion. You can have gravitational confinement. You can leverage magnetic confinement, which is really actually a larger part of the community, magnetic confinement community. How many of you have heard of Commonwealth Fusion? It's one of the main, MFE companies, and they've made some incredible successes recently with their Spark platform. And so we're really excited to see how that moves forward. And then there's inertial confinement fusion. And so the way you confine the plasma can either be gravitationally, magnetically, or with inertia. And that is what we are pursuing here, laser-based inertial fusion energy. And so just to say there's tremendous physics challenges to overcome. Oh my God, right? So we're just going to focus on the simplest. We're taking a deuterium and a tritium. So this is just the proton-proton chain reaction that takes place in a star. And what I want you to pay attention to is the energy scales, level of difficulty, how much energy, potential energy, Coulombic energy you have to overcome to fuse these nuclei together. So we're just going to keep it simple and focus on deuterium and tritium for inertial fusion energy applications. And this is exactly what happened at the National Ignition Facility. And the idea is that what comes out of this fusion reaction is a tremendous amount of energy. Most of it goes into the alpha particle, the helium, but then you've got this 14 MeV neutron, right? And this guy's really helpful because what he does is he helps me to breed more tritium. There's not a lot of tritium, right? But did you know that in 1 tablespoon of seawater, this is pretty crazy, 1 tablespoon of seawater, there's enough deuterium, right? Because we need both deuterium and tritium to power, if you have the tritium, there's enough deuterium in the seawater to power San Francisco for a day, a tablespoon, right? So the opportunity here is just tremendous. It will be, no joke, a global economic game changer. Whoever gets here first, commercial fusion energy will change the world. Just, whew, right? That's huge. So that's why we need to do our due diligence and get there first. It truly is a race. And so that race was kicked off in part at Livermore, and they've been refining, improving, going through the methodical steps of looking at ways to boost what they call the fusion yield over time. And so they started out in 2021, and the idea here is a spherical capsule of deuterium and tritium are imploded, and you need it to be totally symmetric. So you look at these example images, and it's kind of wobbly shaped, right? It's not perfect. And by December of 2022, they're getting really close. So there's been evolution over time and tremendous effort, in part by the scientists and by the lab and by our Department of Energy, and our whole ecosystem of national laboratories and academia have been pushing this forward. Really, it's remarkable to think, for my kids, for your future kids and the like, that this could bring about a new era in how we use energy. And the trade space of waste generated to output power compared to the other nuclear energy approaches is much better. And so I think that's another reason to be thinking about how fusion is the future. One opportunity we've had here at SLAC is to form what's called a inertial fusion energy hub. This is a bit of a busy slide, but we're a part of this hub called the RISE Hub. It's a partnership between different national labs, academia, and several private companies. And there's a QR code up there above our private companies. And if you're interested in learning more about what we're doing here at SLAC in inertial fusion energy, check this out. There's a lot of opportunities for student engagement. Every summer, we have students that come and join us for experiments, for different R&D efforts at SLAC. You get to use big lasers. I tell my kids, you get to blow things up. Okay, sometimes. But it's a lot of fun, and it's a great opportunity to network as well and understand both the science and the technology and engineering. So as part of this hub, I'm in charge of doing a lot of the validation experiments. The idea is that, remember I said, in order to leverage a lot of our simulations and models, you have to benchmark those with data. So part of my role is to dissect what are the appropriate experiments to do and come up with a different strategy leveraging lasers and facilities across the whole globe. And much of my current work focuses on that fusion capsule and the materials used to house the deuterium and the tritium. In other words, one way to keep the DT right there in that perfect spherical shell is to use foam, nanofoam. And foam is used a lot in industry and many applications, but the problem is there are a lot of issues with foam and how they are engineered and understanding their performance characteristics. In particular, materials can be messy, right? They can have impurities, imperfections. And so it's my job to break down what are the appropriate measurements to make at those extreme conditions, right? Not quite to fusion, but leading up to that fusion pressure, temperature, density range, and be able to control the material response. Because what you want is not the picture on the right, right? The picture on the right is showing you an example simulation where a lot of what are called hydrodynamic instabilities have forced this perfectly symmetrical shell holding my DT to have all of these instabilities jetting out. And that's not going to give you good yield. It's not going to give you enough energy to deliver to the grid. So what we've done is leverage our extraordinary resources here at SLAC. In particular, we use a lot of different light sources, but one in particular, the LINAC coherent light source, has really been the crown jewel for interrogating materials at the nanoscale in a time-resolved fashion. In other words, I get to use the LCLS. You could use it, right? You could propose an experiment. And it's like having a 2-meter long camera or a 2-meter long facility that gives you femtosecond shutter speed for a camera. What does that actually mean for materials? You are able to take images and collect information that's shorter than a phonon period, right? Shorter than thermal vibrations. It is a true freeze frame. And so I'm going to combine that exquisite X-ray probe with my big lasers, right? And so I'm going to generate an extreme state of matter using this nanofoam that's holding my fuel. And I'm going to probe what happens to that material. Do I have the correct performance? Is it going to implode or shock up or compress in a way that is predictable and giving me a good answer, improving the compression? So we combine it with an end station called the Matter in Extreme Conditions end station, where I have 2 flavors of lasers, right? One is something called a long pulse laser. That just means I get to compress with a laser that's of order 100 joules. And I actually generate an ablation front. It's really cool. It's Newton's third law. It's perfect. You ablate one side of your target, it generates a plasma. And as that plasma is blowing off, it launches a shock wave in the other direction. Isn't that cool? And so what I'm interested in is the transit of that shock through my sample. And I get to take pictures. I get to probe at just the right time with the LCLS, the X-rays, to witness what is happening to the microstructure of my nanofoam, right? Is it setting up these instabilities? I'll show you that it is, which is irritating in just a second. There's also a short pulse laser that can do, 10 to the 21. How many of you have seen Back to the Future, right? And Doc Brown says 1.21 gigawatts. Okay, he says it wrong. It's giga, but right? That amount of energy that is in a bolt of lightning is what we routinely send to our samples that are about the size of your pinky nail, right? Every day, and every 7 minutes, in fact. Or you could, the dreams of going up to 10 hertz, right? Because it's that rep rate, it's that repetition rate that moves from the 1 shot a day paradigm of the NIF, which was amazing, into being able to deliver inertial fusion energy to the power grid, right? So that is part of what we are spearheading. There's a lot of science yet to be done. I'm going to zip through these. Sometimes we craft samples that are surrogates, right, to understand the physics, distill it down so you're only changing one variable at a time. Here's one where I looked at a void collapsing as a shock transits. There's another one where we looked at a nanofoam and we leveraged this really cool technique called tychography. Okay, it's got a funny name, but here's the beauty. I don't need to know anything about the material. I just look at the diffraction pattern, right? In the far field, there's a lot of details there about what kind of x-rays you need. But the point is, I don't need to know anything about the sample, and I can recreate these beautiful foam images. And I do that in such a way where I collect multiple angles and build up a tomogram. It's amazing. Okay. So scientists are using this to understand the nanostructure of these foams, also as a function of fabrication method. Here's an example where a student looked at a foam specifically for inertial fusion energy that is additively manufactured, right? Because you might think, oh, you know what would be great is if you could just print these things. That's a nice, fast way. It turns out that it's harder than we think, but we're working on it. In particular, looking at how we dissect the density distribution within these foams and that relationship to performance. Okay, you might say, that's cool, you've done a lot of stuff on foam, but what about actually loading the foam with the deuterium and the tritium, right? This is a liquid, not the tritium, we don't work with tritium here, but the deuterium testing, we are undertaking tests for the end of calendar year 2025, coming up in several months, to actually do these studies at MEC. We're using a lot of working with a lot of colleagues, friends, and different institutions across the United States and internationally, and bringing together the right team. That's the other piece, the other message I want to share is that, gosh, does it take a team of incredible scientists. And I am just so lucky to work with so many phenomenal folks who care about the science and executing these experiments. Here's an example of one of those 3D printed foams under shock compression. And you can see in the upper right, there are a lot of lumps and bumps in this feature, right? If it were a perfectly smooth wave and there wasn't anything to worry about, it would be a fairly uniform curvature. But we've got jetting and instabilities showing up in every sort of way. So that's even worse in this example, where you see discrete jetting, so-called Rayleigh-Taylor instabilities forming at the interfaces. So I'm running short on time, but I want to leave you with a few thoughts as we are about to conclude. This is just one example or set of examples in understanding fusion materials that will position us in a strong way to tackle all of the difficulties, the unknown unknowns, right? We think we have the known unknowns, but there are so many aspects of the R&D that are left to be addressed. And so many diagnostics, right? I'm an experimentalist, so thinking about all the different kinds of diagnostics, developing new diagnostics, right? That can address many of our needs. The private companies are also very much interested in how to leverage our, national lab, DOE national lab ecosystem to help them de-risk a lot of those technologies. And so sort of on this roadmap to commercial fusion, there are a number of interesting scale-up and test bed opportunities that SLAC and other labs are participating in. And this really is the future, right? We know of several companies and they have designs in the works for their first fusion pilot plant. In fact, some of those companies are here in the Bay Area, right? Which is really exciting. So again, thinking of sort of this ecosystem, we are a nexus, us and Livermore Lab and other academic institutions are really at a nexus and an exciting point for fusion energy. And this idea that in fact, it's possible to power a city in the simulation land anyway, thoughts that if you were to reparate this fusion energy technology by virtue of laser power or pulse power, that you could certainly take care of a city like San Francisco. Certainly this work could not be done by a single person. It takes an incredible team, and there's a lot of names on here. But just to say thank you so much for your attention. The future is bright. I think that the future of humankind, or the timeline of humankind, is really hung on a series of discoveries. And fusion energy, I think, is likely next. Thank you so much.
If you want to learn more about this topic or other energy topics, visit our Stanford Understand Energy Learning Hub for free resources, including signing up for our monthly Energy Spotlight. Don't forget to subscribe to our YouTube channel and tap the notification bell to be notified for our newest content.